Yes, good morning. Good morning, students. So today we'll see reaction intermediates, right? So generally, these reaction intermediates will be studied in organic reactions. So whenever the reaction takes place, uh, it can be converted into reactants can be converted into products. So first the reactants can be converted into intermediates. First it will be converted into intermediates, and the intermediates will be converted into the products. So whereas intermediates are reaction inter. So this is called as reaction intermediates. So these reaction intermediates these reaction intermediates are unstable and we cannot be isolated. And once the reaction intermediates are formed, the reaction will take place very fast and these reaction intermediates cannot be extracted. Right? So this will be a hypothesis. This is called as a hypothesis. So we cannot be isolate these reaction intermediates, but reaction intermediates will be exist. So most of the organic, first we'll see the reaction intermediates. So in generally in organic chemistry, available intermediates are carbocations, carbanions, free radicals, and carbenes and the nitrates. So these are the some examples of intermediates. So first intermediates means before converting it to a product, there is a formation of intermediates and then they will convert it to products. Right? So most of the organic reactions occur through the involvement of certain chemical species. So these are generally short-lived. That is 10 to the power of minus 6 seconds to a few seconds. So this will be very short-lived and short-lived and highly reactive and hence cannot be isolated. So because of this are highly reactive, we cannot isolate and we cannot separate it, and highly reactive and hence cannot be isolated. Even though in some organic reactions we can show in mechanism. So when you are writing the mechanism, these intermediates can be shown, but these intermediates cannot be separated. So these short-lived, highly reactive chemical species through which the majority of organic reactions occur are called reactive intermediates. So these are called reactive intermediates. The short-lived, the highly reactive chemical species through which the majority of organic reactions occur are called reactive intermediates. So most of the organic reactions will occur through the reactive intermediates only. So we know that there are some examples of this. One is carbocation. Carbocation means carbon containing the positive charge. So carbanion ions means carbon will have a negative charge. Free radicals. So free radicals means when the homoelectrical fission takes place, one free radical, one electron will be there on that compound, that is free radical. One unpaid electron will be there on the compound, that is called free radical. You know that free radical and carbocation, carbanion are highly reactive, and carbenes and nitrates. So these are the examples of reaction intermediates. So we'll see step by step. So what is the properties of that each intermediate. So each intermediate of this example is given below. Right? So we'll see carbocation. So first one we'll see the carbocation. So carbocation bearing a positive charge on carbon and carrying 6 electrons in its valence shell are called carbocations or carbenium ions. So this is also called as carbocations or carbenium ions. So by electrolytic cleavage of covalent bond, which the leaving group takes away with it the shared pair of electron. So for example, so we can see, so these carbocations can be formed by electrolytic cleavage. So we know that the bond fission will take place because of by homolytic fission and heterolytic fission. Right? So but these carbocations will formed by the heterolytic cleavage of the bond. Right? So we can see the leaving group will take away the electron, uh, take away the electron, and it will get the negative charge, right? So by heterolytic cleavage of the covalent bond in which the leaving group takes away within the shade pair of electron. So this one, so this leaving group here in this one, tertiary methyl chloride. So in this one, leaving group is a chlorine. So chlorine will take away the electron. So here the sharing, the covalent bond is not equally shared. So this is called heterolytic fusion. Right? So one will get the negative charge, one will get the positive charge, whereas the chlorine will get the negative charge because of the electronegativity of the chlorine. Right? So when this type of bond cleavage will take place, and there is a formation of, formation of, this is a carbon. So this, which one it is formed is carbocation. Right? So this is called formation of tertiary methyl carbocation is formed. So this is one of the interpretation. Right? So what is the stability? So the stability of carbocations follows the order. So tertiary carbocations will have high stability when compared to the secondary, when compared to the primary, and when compared to the methyl. So here we can see that tertiary carbocation will have highly stable because 3 carbons are attached to this one. So when the 3 carbons are attached to this one, the positive nature of this carbon increases. As the positive nature of this carbon increases, so this will be very stable. So whereas in tertiary carbon there are 3 carbons are attached, whereas a secondary carbon 2 carbons are attached. So tertiary means, so these 3 carbons are attached means the positive character of this carbon will have 3 positive characters is attached. So second one it is a 2, the third one it is a 1. So we know that carbon will have the highly positive nature when compared to hydrogen. So whereas in methyl, so methyl will have the least stability when compared to tertiary alkyl, right? Tertiary carbocation, right? So the order of stability can be explained on the basis of the following factors. So this order can be explained on the following factors, that is inductive effect, resonance effect, and hyperconjugation effect. So we'll see this order follows that tertiary carbocation is highly stable. So secondary is a less stable when compared to the third one, and it is follows the first one and follows the methyl. So the order, this can be explained by taking the example of inductive effect, resonance effect, and hyperconjugation effect. Right? So we can see what is the inductive effect, right? So the more the number of alkyl groups on the carbon atom carrying positive charge, right? More the number of alkyl group, more the number of alkyl group on the carbon atom carrying the positive charge, greater would be the dispersal of the charge, and hence more stability would be the carbocation. The stability of the carbocation decreases in order. So the stability of the carbocation decreases in order: secondary, primary, secondary, and the tertiary, secondary, and the primary. So because the positive character is here, the 3 methyl groups are attached to the tertiary, 2 methyl groups are attached to the secondary, and only 1 methyl is attached to the primary, and there is no methyl group is attached to the methyl carbocation. Hence here the positive nature of this one will be very less when compared to the primary, secondary, and tertiary will have the highly positive nature. Hence the tertiary will be more stable. So another important thing is which one is a more stable means that is a less reactive. So more stable means more reactive. So if we see the reactive order, as a tertiary carbocations are stable, less reactive. As the primary carbocations are less stable, high reactive. Right? So when this is the understand, we can understand. If it is stable means it is non-reactive. If it is non-stable means it is reactive. Right? So this is about the inductive effect. The stability decreases as so what is the The relation between the inductive effect, stability decreases as plus I, inductive effect. Plus I is denoted by the inductive effect. So stability decreases as plus I effect of the alkyl group decreases. Right? So this one methyl. Right? So next one, resonance effect. So resonance effect. Carbocations in which the positively charged carbon atoms is attached. Carbocations in which the positively charged carbon atom is attached to a double bond benzene ring are stabilized by resonance. So when it is attached with the benzene ring, so then the resonance effect will be more. So or it is conjugated double bond, so it will be more. So more the number of phenyl group, greater the stability. As a more number of phenyl groups are attached, so more stability. So we can see here triphenyl carbocation is highly stable when compared to biphenyl carbocation and phenyl carbocation. So as the number of rings increases, benzene rings increases, so the resonance effect increases. So resonance effect increases. As the resonance effect increases, the carbocation will be more stable. So here it has a less number of rings, so there is a less stable. Next is hyperconjugation. So hyperconjugation. Tertiary methyl carbocation has 9 alpha hydrogens and hence 9 hyperconjugation structures. So tertiary methyl carbocation has 9 alpha hydrogens and hence 9 hyperconjugation structures. Right? So the stability of various carbocations decreases in order. Stability of various carbocations decreases in the order. So this is tertiary carbocation. This is triphenyl carbocation is greater than diphenyl carbocation is greater than phenyl carbocation, and it is right. So this increases the order, and least it comes a triple bond. The reactivity. So as we discussed before also. So what is the reactivity? Right. So reactivity. The order of reactivity of any chemical species is reverse that of its stability. Therefore, the order of reactivity is carbocations follows as primary carbocation is uh, highly reactive. Primary carbocation highly reactive when compared to secondary and compared to the third one. So whereas primary carbocations are highly reactive when compared to the tertiary carbocation. Because tertiary carbocation is highly stable means it is a less reactive. Right. So orbital structure. So orbital structure of this carbocation. So the 3sp2 hybridized orbitals of this carbon form 3 sigma bond with monovalent carbon, or groups lie in plane or inclined to one another at an angle of 120 degrees centigrade. So these three hydrogens will be formed in 120 degree angles. So the 3sp2 hybridized orbitals of this carbon form 3 sigma bonds with monovalent atom or groups lie in a plane inclined to one another at an angle of 120 degrees. Right. So this is an empty orbital, empty p orbital. Right. So this is one sigma bond formed here. So one sigma bond formed here. S and P2. Yes and P2, and this is empty p orbital. Right. So this is our orbital structure of carbocation. So next we go for carbanium ion. Carbanium ions. So chemical species bearing a negative charge on carbon and possessing 8 electrons in its valence shell are called carbanion ion. Carbanion ion. Excuse me. Carbanion ion means it will have the 8 electrons in it and it will has a negative charge on the carbon. So you can see the example of hydroxyl ion will become acetaldehyde ion, and hydroxyl ion and acetaldehyde ion forms water, and acetaldehyde plus carbocation. This is the formation of carbocation. Acetaldehyde carbocation. So amide ion is reacted with acetylene. There is a formation of ammonia and C++CH. So this is carbanion ion. And stability. So we can compare with the stability and inductive effect and resonance effect. Okay. So stability. The stability of simply alkyl carbocation follows the order. So primary methyl. So methyl carbanion ion is highly stable when compared to the primary, compared to the secondary and the tertiary. So methyl carbanion is a highly stable. Methyl carbanion ion is a highly stable when compared to primary, secondary and tertiary. So when compared to the resonance effect, so the allyl and benzyl carbocations are stabilized by resonance. Right? So benzyl carbanion is stabilized by resonance. So because of this resonance structure, it is a highly stable. So whereas this phenyl is you can see the stability order of this resonance structure, and carbanion you can see the stability order. And so when the two rings are there, so the resonance will be very high and it will be very stable. So whereas if you have one ring, so it will be least stable. So yes, character. So the stability of the carbanion ion increases with the increasing S character of the carbon carrying negative charge. So we can see that C1C and methyl 50% of the S character here, the 33% of the S character and 23% of the S character. So the stability of carbanion ion increases. So as a S character increases, so the character of the S as the carbanion ion increases. So S character is directly proportional to the stability of this carbanion ion. Okay. So reactivity. The order of the reactivity of carbanion ions is reverse of the order of the stability. As we discussed, so tertiary we may have highly reactive when compared to secondary when compared to the primary and the. So orbital structure. The structure of simply alkyl carbanion ions is usually pyramidal. So just like those of ammonia and amines, so the carbon atom carrying the negative charge is sp3 hybridized. The carbon atom carrying the negative charge is sp3 hybridized. 3 of the 4 sp3 hybridized orbitals form 3 sigma bonds with monovalent atoms or groups, while the 4 sp3 orbital contains the lone pair of electrons. So the carbanion ions which are stabilized by resonance are planar. In these carbanion ions, the carbon atom carrying the negative charge is sp3 hybridized. So carbanion ion is sp3 hybridized. Thus, whereas dimethyl carbanion ion is pyramidal, allyl carbanion is planar. So orbital structure of the carbanion ion. So orbital structure of carbanion ion. So you can see there are 3 sigma bonds and there is a one lone pair electrons here. So this lone pair electrons is responsible for forms of the carbanion ions. So free radicals. So you know the free radicals means lone pair electron present on the carbon. So these free radicals will take place when the homolytic fusion takes place. So example, in fluorine, the free radical may be defined as an atom or a group of atoms having an odd or unpaired electrons. Right? So when chlorine will undergo homolytic freezing in the presence of UV rays or the heat, so there is a formation of chlorine free radicals. Right? So these are primary free radicals and secondary free radicals and tertiary free radicals. So the order of the free radicals is the same as the carbocations. How the carbocations order will have the tertiary as the most stable and the secondary will have the most stable when compared to the first one. Right. So here you can see the example. Tertiary group methyl free radical has a greater stability when compared to the isopropyl free radical when compared to the ethyl free radical compared to the methyl free radical. So the stability order of the various free radicals in the order you can see this one. And so orbital structure of these free radicals. Orbital structure of this one is alkyl free radical like carbocations are planar empty spaces. The only difference being that in carbocations the unhybridized p orbital is empty, while in the free radicals it contains the odd electrons. You can see the orbital structure. So it is a 1r and one p empty orbital. So this is a sp2 hybridized carbon. So this is a sp2 hybridized carbon. So whereas the r and will have the 120 degrees degree. Yes. So next class we will see the mechanism of substitution reaction. Next class we will see.